Okay. So the last topic for mirrors is the mirror formulas. And let's look at a concave case. And let's say that this is the focal point, and this is the center of curvature. The distance from the focal point to the mirror, that distance right there, is usually denoted with a lowercase f. And that lowercase f is the focal length. That's the distance from the mirror to the focal point. So this is the focal point where all the light would converge. And this distance from the mirror to there is the focal length. The distance from the center of curvature to the mirror well, think back to the circle. If it's a spherical mirror, what's the distance from the circle to the center of the circle? Yeah, r for radius. And we sort of been saying this first relationship all along, but now we're going to actually put it in the formula. What's the relationship between f and r, the focal length and the radius? Exactly, 2f equals r. Or more popularly, it's stated r equals, no, f equals r over 2. Ready? Again, this whole arrow right here is the object. And this whole arrow right here is the image. Yeah.
That means there's a different formula for each situation.
No. The same formula is going to hold. Good point. If you check out the distance from the object to the mirror, d sub O. If you check out the distance from the image to the mirror, d sub I. Two more measurements, and then two more formulas. I'm just going to put this on a separate diagram because the other diagram is getting a little full. So again, if this is your object, and this was your image, the height of the object from the feet to the head is called h sub O. The height of the image from the feet to the head, right in there, is h sub I. So h sub O is the height of the object, h sub I is the height of the image. So then finally we have our equations. One over the object distance plus 1 over the image distance equals 1 over the focal length. And it works for all cases of concave and convex. But the only thing tricky about this formula is when the values are positive and when the values are negative. And the rule goes like this. DO is always going to be positive. DI and F are positive when they're real and not virtual. For concave, yes. D sub I is going to be negative for the concave case when the object's in way, way close. For the convex mirror, D sub I is always negative because there's only that one case. For the focal lengths, a concave mirror, the first batch that we did, those focal points were real. So the focal length is going to be positive for concave. But for convex, it's a virtual focal point, so the focal length is always going to be negative. All right. The last formula, actually, two. M is the magnification. And the magnification is HI over HO. The height of the image divided by the height of the object. But that's also equal to negative DI over DO.
What's M?
M is called the magnification. Of the lens. Or I'm sorry, of the mirror. Yep. Now, here's the tricky thing. There's two different rules for the positive negative business. Okay? We talked about the positive negative business rule for the image and the object distances, yes? Okay? If it's real, positive values, and if it's virtual, negative values in there. Yes? So for DO and DI, real, positive values, virtual, negative values. But for HI and HO, it goes by its own rule. If it's upright, it's positive, and if it's upside down, it's negative, which is really the opposite rule of this. If you go back and look at it, so in summary, all the formulas involved here are as follows. F equals R over 2, 1 over dO plus 1 over di equals 1 over F. And by the way, that does not simplify to dO plus di equals F. You know, you got to do it, you know, the reciprocals. And then magnification equals HI over HO, or magnification equals the negative of DI over DO. And then, of course, you can put those two together and you can get HI over HO equals DI over DO. Oh, yes, yes, thank you. Thank you. And that completes the mirror segment.